Okay, so in order to use the intermediate value theorem, we need to talk a little more about continuity. How would we explain how we know that a function is continuous on a closed interval a to b? And so for our purposes, we're going to keep this really simple. And in fact, I've got a document on Moodle labeled continuous functions that's going to have all this information in more detail. But for us, basically, we're going to just say that as long as they're defined, functions we're familiar with from previous classes like college algebra and pre-calculus are going to be continuous at the places where they're defined. All right, so the way we're going to say that, just in summary form here, is the following functions are continuous on their domains. In other words, i.e., they are continuous on any interval on which they are defined. Okay? And so, first of all, familiar functions from like college algebra or pre-calculus. So just a couple of examples here. Things like y equals x squared plus 3, familiar function from algebra. Y equals square root of x, another familiar function from algebra. Y equals natural log of x from pre-calculus. And maybe something like y equals tangent x, also from pre-calculus. All right, so those functions are going to be continuous on any interval as long as they're defined on those intervals. And this function is defined everywhere, but the rest of these functions are not. So that is something we'll have to be a little bit careful about, thinking about where those functions are defined. So these familiar functions are continuous on their domains. And second, functions built from continuous functions. Okay? And there's a couple different ways you could build these. First of all, so I'll just say part A, by arithmetic, like you add two of these kinds of functions, or subtract them, or multiply them, or divide them. And so, for example, y equals x squared times natural log of x is built from this continuous function and this one by multiplication. Another example would be something like y equals square root of x minus tangent of x. That's built from these two continuous functions by subtracting. Okay? And the other way to build further continuous functions is by putting one inside the other one, which is called composition. Okay? And so, for example, we might have something like y is equal to natural log of x squared, right? So we took the familiar function natural log x and the familiar function x squared, and we put the x squared inside of the natural log. Okay? So any function like this is going to be continuous on its domain. So for example, we can say something like this. The function y equals x plus square root x is continuous on its domain, which is, well, what are the x values we're allowed to plug in here? We can plug anything in here, but only numbers bigger than or equal to 0 here. So its domain is 0 to infinity, including 0. Okay. So, of course, this means that this function is also continuous on any interval contained in this domain. So we could also say something like this function is continuous on the interval 1 to 2, right? Because that sits inside of the domain there. Let's do another one. The function, let's see, how about y equals, let's take this one actually, x squared times ln of x is continuous on its domain. Which is equal to everything from, let's see, so we can plug anything into x squared, but remember you can only take natural logarithms of numbers that are bigger than 0. So we're only allowed to plug in numbers from 0 to infinity, this time not including the 0. Natural log of 0 would be undefined, just like log of a negative number would be undefined. Okay, so those are just a couple of quick examples there of how we know functions like this and this are continuous.